In this problem, we're going to solve for the equation of motion for the harmonic oscillator using the Hamiltonian. To do this, we start with the Lagrangian. In the last problem, we learned that the Lagrangian for a harmonic oscillator is really just a spring and a mass on the end, and there's our x-coordinate, measuring from the point of equilibrium. Our Lagrangian is our kinetic energy minus our potential energy. Now, one thing to notice about the Hamiltonian is that it's written in terms of the generalized coordinate and the generalized momenta. In contrast, the Lagrangian is written out in terms of the generalized coordinate. I wrote out x, but we could have just easily written q, and x dot, not the generalized momenta. Hence, our Lagrangian is in terms of x and x dot. Now, in order to solve for the Hamiltonian, we need to do two things. First, find the generalized momenta. That's going to be p equals the partial derivative of Lagrangian with respect to x dot, because q is our generalized coordinate, which in this case is x. The derivative of this, partial derivative of this with respect to x dot becomes, no x dot here, so we ignore this. Just this term becomes m x dot, which now is what we'd expect. Momentum is normally thought of as mass times velocity. So next, we involve this transform. So it means our Hamiltonian becomes the sum of the time derivative of our generalized coordinate times the generalized momenta. We only have one coordinate in this case, so we can write out, let's see, our generalized momentum is x dot. Q dot is x dot in this case, so we simply mx dot times x dot, or let's put mx dot squared, minus the Lagrangian. So we have 1/2 mx dot squared minus 1/2 k x squared. If we simplify this, we get 1/2 mx dot squared plus 1/2 k x squared. You'll notice that our Lagrangian was t minus v, and our Hamiltonian just became t plus v. This is not always true, but if we've satisfied two conditions, we can just make this shortcut that Hamiltonian is t plus v, or in general that the Hamiltonian really is energy, and that h really is equivalent in some respects. Now, this is not always true, so use this with caution. Now, we can make this shortcut right here if, on two conditions, if one, we do not mix, and no terms that mix x, x dot, x double dot, or so on, for any of our generalized coordinates. Second, that there is no explicit time dependence. No explicit time dependence. If we can satisfy those two, then we can just write H equals kinetic energy plus potential energy. Okay, now we have this. We have one step left. We did this one. We did this one. Now we need to combine the two because H must be in terms of Q of our generalized coordinate, Q, or in this case, X, and not X dot. We need to replace all our X dots with the generalized momenta. That means we get P squared over 2m plus 1/2 k x squared. This is the Hamiltonian. Our next step, take this Hamiltonian and apply Hamilton's equation. Apply it to Hamilton's equations to it. So we will take first the derivative with respect to p, the partial derivative with respect to p. We get p over m. We set that equal to q dot. Our q is x in this case, so we get x dot. Likewise, we take our second equation, derivative with respect to x, that's what q is, and we get, that would be kx. We set that equal to negative p dot. We now have two first-order equations, which is why, in general, many people prefer to use Hamilton's equations because the two first-order equations make the problem easier to solve. In order to get our equations of motion, we need to combine these two equations. We can do that by taking the time derivative of this and substituting it in here. And we will get kx equals negative mx dot, which is exactly the same formula for motion we got in the Lagrangian. In which case we have the generalized answer for this, a cosine square root k over m t, some phase factor if you want it, usually set it to 0, is the equation of our motion. Because sines and cosines are solutions of this equation.